something which is certainly very important, and deep neural network function is an extraordinary class of functions with extraordinary properties. And so how do we understand this high order of convergence, or something about metric entropy? We find something very relevant. So we're talking about a set of Banach space B. So the metric entropy would be this number is this you take you have two M balls to cover the of size epsilon, radius epsilon to cover this set. You take the kind of with two M ball to cover the so that how much of accuracy you can get. For example, if you have an interval of where's the chalk? Okay. If you have if you say you encoded an interval, something you approximate the interval, you cannot approximate infinite many points, right? You just put some point here. With the epsilon size. So all these points you put in there, that's how I encode in this interval. Any other place I can take a nearby and say that's my representation. So I'm sorry. This is what measures how accurate the element can be specified with n bits. This basically, if you have a long interval, you have need many more points. You have with epsilon size. Okay, that's the. In general, if the Banach spaces, you can measure by the unit ball. About the ball of radius epsilon. And we do the 2n is because we have the binary system in our computers these days. High dimensional sets does not always have larger entropy. Why? If my cube in the large interval is like R, if R is very small, it could be smaller than the unit interval of one dimension. Or if a unitary cube in high dimension, maybe not necessarily more difficult than the large interval in one dimension. I don't know if you get my idea. So it's really the relative size of the set. So if you're talking about high dimensional functions, if it's a constant function, in high dimension, it's still pretty easy to approximate. If you're talking about a high dimensional function, which is extremely smooth, or like a linear function, is not. So this is the metric entropy is one way to measure these things. Okay, now if you tell me why they said the Sobolev space is not the right space, for example, if you take the metric entropy for if you have 2n ball to cover this unit ball in the WSP, you get to n to the negative s over d power. If d is very large, the n 2n balls cannot do much of a good job. That's what people call the curse of dimensionality. This is because of this Sobolev space with a fixed s. It's too big. The function class is, we're talking about unit ball, okay. Now if the ball size is very small, if my Sobolev norm is very small, then it's a different matter. Do you get the idea? Well, the question here is that if you're talking about wavelets, you're talking about adaptive finite elements, it's about the Olga mentioned this approximation function class, like this, something like that. If you have certain, this is approximation theorem, if you have certain discrete space, it would correspond to a certain functional class so that you have certain error estimate. Now the question that this function class, sometimes it maybe require less regularity. I don't know if you guys paid attention to something called sparse grid. And for many years, sparse grid, many people work on that. If you look at the approximation class, you have all the second order derivative on each variable, right? Then you take a lot of derivative. That's a functional class. If that norm is bounded, then somehow the sparse grid will do a good job. There's a very little curse of dimensionality there. So you need the function class to be not big. In one-dimensional problem, I can make it very big. In a high-dimensional problem, I can also make it very small. You get the idea? So the curse of dimensionality, when we talk about that, we have to keep that in mind. And for so-brief space, if you're telling me, okay, if you're in high dimension, okay, my S is equal to 10. So you take a unit ball in W10P with high dimension. Trust me, that's a function class contains a lot of stuff. In there, you have curse of dimensionality. Does that make sense? So if you take a spatial polynomial for degree of freedom of n like this, does a spatial polynomial has a curse of dimensionality? With n degree of freedom, you still get a negative S over D. Yes, if my so-brief derivative is like S equal to 10 or 2, you have cursive dimension. You can also do other like radial basis by Gaussian kernel. You can also do this sort of things. Okay, you also have the reproduced kernel Hilbert space source. That kind of space. You require smoothness. So, but what if my function is sufficiently smooth? If you take my S equal to D, half of D, would you say you have a curse of dimensionality? I have n to the negative. I have half. Yeah, but I say that. So if I have a D, 2D, but this is a D and a half. If some people look at this Baryon norm, is people get excited about it. F of hat of 1 omega. Then they put over 1 plus 1 omega. Maybe an S here. In order for this one to be bounded by some kind of so-brief norms, and even for that guy, you need to deal with 2 number of derivatives. If you want to embed these things, how do you do this? If you do this f of hat of an omega, if you want to do the embeddings, okay? Wait a minute. You want it bounded by some kind of 1 plus an omega of d and f of hat an omega of square d of an omega, right? And put an s. If you took the Schwarz inequality, that's 1 plus of an omega negative s. Let's do a Schwarz inequality, okay? And this is the so-brief norm, right? Did I do the Schwarz inequality correct? I think so, yeah. So So in order to have this one to be bound, you do your math. S has to be sufficiently large, right? If you do the, and in general, you get a d over 2. And but if you just do, of course, this looks harmless. When you see these things, you don't need that many derivatives, but it's L1 norm. I asked the harmonic analysis people, what do you know about L1 norm Fourier transformation? They said it's very little is known about these things. And you can do Schwartz inequality to do the Sobolev embedding. You figure that you need a lot of derivative to bound this guy here, okay? And so in general, you probably need a d over 2 derivative. But of course, that's I think this baryon space or this neural network space has a little bit of weaker regularity kind of requirement. But you still need a lot of derivative if you want to really relate by the Sobolev norms, okay? Does that make sense? So if you do polynomials, if you have sufficient many derivatives, then I also get an n to the negative. I can get n to the negative any power if you give more derivative here. But of course, there's something in front of that guy also depend on dimension. There's several places that depend on the dimension. You have the exponent depend on dimension. You have this Sobolev norm. This norm also depends on dimension. This constant in front of it, sometimes you get an exponentially dependent dimension. So you have at least 3 places you have dependent dimension. But no matter how big, if my norm is sufficiently small, if my norm is very, very small, this is my ball size is very small, then you can be small, right? But of course, you can also do this sort of, but you can also do the same kind of analysis for all this space here. You know, how do you encode in this this neural network functions? The neural network function, we also did the analysis. If you want to do, this is the cosine, the exponential. This is the polynomial, the Relu to the case power. You get the n to the negative half. If you have the unit ball, you still so this functional class, this variation space, is the right functional class. If you have a magic optimization algorithm, can get it. I think in theory, you have, if the function is stay in this class, the norm is not big, it's encodable, it's doable, it's theoretically doable. But again, this functional class can be very small. It has to be small. Relative to the dimension. The dimension make it very easy to be a bigger class. Okay, but all this function just because I'm running behind the schedule a little bit, but there's Olga yesterday mentioned about this oscillation business. We actually have some slides here to have a theoretical explanation of this business. I'm going to tell you one thing here. For those of you who know multigrade method, this is the hierarchical basis in the finite element method. This hierarchical basis has this magical identity. This hierarchical basis is a composition of, if you do composition of this one, you get this one, you get the 4 composition, you get this one. So the hierarchical basis, if you use the hierarchical basis together as one function, you get some kind of a very high order of convergence in terms of the for example, you take the x squared, you can approximate, you only need, you have exponential convergence. You have you have a logarithm. Let me see, I just want to, let's see. Yeah, if you take these sawtooth functions as a basis, if you use this as a basis function, as a one basis function, okay? This is one function, that's the second function, this is the third function, this is the fourth function. This is all the fourth function. If you do these things as one base function, you can approximate this x squared exponentially accurate. Given that, you can also do that for, you can explain this to, polynomial, very smooth function. What's the message? The message here is that by composition, it is possible to, with only error degree of freedom, you get exponential convergence with piecewise linear functions. But you do not use this height function as a basis. You get a collection of height functions as a basis. Well, I'm telling you because because I want to understand. People hand wavelength to oscillation. We have some rigorous mathematics actually tells you that if you use this basis function if you this things as your basis function, you can get exponentially convergence for smooth functions in 1D, even in multi-dimension. And so the composition and all that has some remarkable property. I mean, again, you talk about complexity. This is globally supported, dense matrix. But at this point of the game, the computational complexity, we're too busy to worry about that because it's an important issue, but it's not something on the agenda yet. Because I'm going to address to you later this neural network functions has rich approximation properties, but how do you realize the approximation properties is extremely complicated problems. Because this is a long linear set, it's not a basis. It involves highly long linear, highly long convex optimization problem, which how do you get the things to converge? That is, of course, it's a huge open problems in this business. And the good news is that I'm actually certainly very intrigued, impressed by the fact that the ChatGPT these days, I'm getting very interested in myself. According to the theorem, I can prove ChatGPT should not be as good as today, but I guess my theory doesn't really speak very much. And anyway, I'll make that point something later. So I think I'm going to wrap up these things about approximation theory. And sorry, I was very quick on the hierarchical sawtooth business, but I was just telling you, at least through this lecture, what's the message I'm giving you. Deep neural network Relu is a natural generalization of finite element method. I hope you're convinced of that. And Relu DNA is nothing but identical to linear finite element method. And but they have difference as a set of functions. They are identical, but they have total different structures. One has grid, another one has not even points. So it's pure algebraic, the other one is geometrically constructed. And so you need a certain number of depths, certain amount of depths, because with sufficient deep neural network, Relu can reproduce any adaptive finite element method. And with Relu to some power k greater or equal to 2, and you can reproduce any polynomial of any degree when you go deeper. So the depth is important. I also showed you the example which I didn't really show you, that if you use this sawtooth things, if you go deeper, you can get an exponential convergence for good functions. And all that. But the thing is that in terms of approximation property, to understand it, to appreciate this, you do have remarkable approximation property that similarly seems to have no cursive dimensionality. But the story behind it is interesting. When you number of parameter as a metric, we have to be cautious. If that one single parameter contains 1 million digits, then you probably to be careful. This thing was about Lipschitz function. When if you have Lipschitz function, there's a beautiful result that if you take a Lipschitz function with n variable n negative 1, if you do neural network, you get n to the negative 2. So why is that? But if you count the bits, it's the same. There's nothing. You don't gain anything new. Just go read their paper. If you read it, you read n, the number of bits will be square. And but nevertheless, it's very interesting. But deep neural network is remarkable. I'm going to just wrap up this. I don't have any questions here. We can pause here for.
Is there any questions?
Thank you for the talk. So in these discussions about this curse of dimension and so on, we always have these spaces with homogeneous derivatives. They are very isotropic in the derivatives, but there are these other spaces in which there are anisotropic degrees of different levels of derivatives in different directions. And I'm wondering if there are results in that direction to kind of maybe try to mitigate the curse of dimension, a bit like in sparse grids and so on.
Yeah, I think this is an extremely interesting question. Thank you very much. And one to answer your question is, let me repeat this sparse grid method. Sparse grid method, the requirement of the regularity is highly anisotropic. You take the derivative of very special kind, and I remember in those days, for example, Harry Isrintant is a good friend. He's doing the hierarchical. He proved that if you, on the certain class of Schrödinger equation, the solution actually belongs to that functional class. Highly anisotropic regularity requirement. And so for this one here, I don't see any derivative here. So you really have to study this L1 of some sort. Or maybe you can put some power here. And that's in the Fourier space. And this has to do, is what I call the Byron space for the exponential function. I call it spectrum Byron space. The variation space, which I introduced earlier, is a weaker space than this. And that's inherently, implicitly requires certain anisotropic kind of smoothness there. But again, I do not know the answer to your question. I don't know. I think I'm so sure many people are studying this. I wouldn't be surprised at the results there in the literature. But the interesting question here is that to have a different way to answer your question is that if you solve a partial differential equation, if you claim you can solve a high-dimensional PD by deep learning, okay? So you better show me you have some regularity in terms of this kind of norm, or maybe variation norm. If you can, like what Harry proved, if you are, again, this sort of the regularity requirement, it seems to me, is weaker than the polynomial, or I think I even have some slides. It's weaker than the sparse grid. But how much weaker actually we can actually estimate by the metric entropy is not much weaker. The metric entropy, if we estimate that, it's only differ, it's all have n to the negative half there. So the difference is something over 1 over d. So the gap between those spaces, in terms of the metric entropy, they are very small. So in that case, there's not much room you can hope to improve, really. On the one hand, I cannot answer your question to really identify the anisotropic semi-regularity. But on the other hand, I can also tell you there's not much you can hope. because of the metric entropy estimate, the difference between this subgroup space of very high order, isotropic regularity, or with this one, they are very small. The gap is smaller when the dimension is getting higher. I don't know if I answer your question.
I propose to move to the next question.
Yeah, there's a.
Thank you for the talk, very interesting. And my question is about the choice of the parameters of the neural networks you use as a base, as basis. And how are these parameters chosen? Is there to define the basis, you consider any parameters, of course, but in the solution computation, how are those chosen? Is there some kind of optimization training strategies?
Very good. Thank you very much. I'm actually going to talk about that a little bit, and we have a theory when you have when the Relu to the case part. I told you that you cannot. I have this condition that this condition sigma ai is less or equal to m. I control the size of the parameter. I told you if you don't control the parameter size, this n doesn't mean anything. N equal to 3 is enough. So you under this condition, we call a stable manifold, a stable neural network. We have the best approximation. We have an optimal order. You cannot improve. You can lower bound and upper bound. It's n to the negative 2.5 minus 2s plus 1 over 2d. Is in the 2k. If you reduce to the k's power, it's the N2 norm. Okay. And this is the rate of convergence. Now the question is, how do you achieve this rate of? That's your question. And if you take the optimization problem, if you solve the global optimization problem, you get it right because it's my inf. But you never get this. It turns out I have an algorithm you can get it. I will show you in this lecture. This is the very important question.
Okay, thank you.
Yeah, there's another question somewhere.
Any other questions?
There's a question here.
I just wanted to bounce back really quickly on the first question of Olga. Was it Olga, I think?
Yeah.
Yeah. I think there's a bunch of papers on Korobov spaces and Besov spaces and all of these things that show the approximation properties of deep networks and give rates. But the message here is like, they don't beat sparse grids. People just show that sparse grid can be approximated by deep networks, and then you work over almost the same rates, but that's all. So,
okay.
Yeah.
But actually, I have an argument showing that even the shallow neural network, it will beat the sparse grid somehow. And yeah, I think that's in a very real resonance what I just said, that all these things requires very high order regularity implicitly. And they are about the same order. If you do the sober embedding of the stuff. And somehow this deep neural network is always the inequality on the left. The one on the right is a sober space. And you can imagine now how much smaller is again, based on a metric entropy estimate, if the higher dimension, there's not much room you can do. Anyway, it's an interesting, highly open area. Yeah.
Okay, I propose that we move to the next part of the course and postpone the discussion to the lunchtime.
Thanks for all this interesting question. It's such an interesting research field because basically very little is known. Now you do iterative method. Okay, I'm going to, so I only got half an hour. If you do iterative method.
You have an hour. No. 1 hour.
1 hour? Okay. Okay. I can stop anytime. I can talk 10 more hours. The reason I got into this business is because of the iterative method. Because I'm going to show you very quickly. Maybe in this lecture I'll be a little bit fast, and if you want, slow me down, slow down, you can raise your hand, okay? Because I want to give you some idea. There's so many things going on in this business. So I look at the thing in the iterative kind of angle, because every mathematician, when you want to look at a neural network from his own angle, but you do iterative method to solve a linear system equation, okay? So the way is all correct residual. And I want to emphasize, because one of the big deal in deep learning is resonate, residual neural network. The resonate, all the iterative correct residual. If with resonate all this, you can make very deeper things, since you don't screw things up. The resonate, as a matter of fact, is motivated by multigrade method. So you basically form the residuals, you solve you do iteration, look at the residual, you solve it, you equal to f. You solve this residual equation approximated, and you do an update. So that's pretty much how the linear iterative method go. Now the question is that how do you solve to choose B? So the way to choose B here is that you can choose, for example, if you do the matrix decomposition, lower triangle, upper triangle, diagonal inverse, you get a Jacobi or L plus 1 D inverse and all that. So the basic iterative method we call the Richardson iteration. You approximate the inverse by a number. So that's the simplest method in the world. You approximate the inverse by one single number. Or you approximate the diagonal inverse. You put the lower diagonal inverse, do some relaxation and all that. Now our beloved gradient descent method. This gradient descent method is the method of the town. Okay, the machine learning uses gradient descent, and it's because it's the simplest. And the gradient descent method is the simplest iterative method in the world, because you approximate the inverse by a number, which is called a learning rate. If you do it's the Richardson iteration. If you take the gradient is this of this guy, it should be a minus a negative gradient. Actually, sorry, the gradient descent. It should be you write this as negative gradient. Okay, it's a negative gradient. The gradient descent is you can do a scaled gradient descent method. So at least do a diagonal scaling. But somehow, well, there's something called Adam method. They want to do the scaling in some very funny way. And again, that Adam really dominating the field. Gradient descent. That's their method. That's their machine learning method. Now the question is that for mathematicians like us, okay, why people care this method so much? But, so I'm going to give you some example, and I'll give you this example. This is going to be in the computer lab session. I want everybody to actually code this number to, if you care about it, do some analysis. Okay. So I like this example for several reasons. Again, if you have any take-home message, this is one of them. And you got to code this one. Okay, you do a 3x3 matrix. This is a semi-definite matrix. And it's a singular matrix. You can imagine that in machine learning image classification, if I shift my image from left to right a little bit, it's still me. Translation invariant. So this example, you have this eigen zero eigen function, which is a constant function, which is row sum equal to 1. I take the right hand to be the range of A0, and I do a perturbation of the ones. So if epsilon is positive, this is symmetrical positive definitely. Otherwise, it's a singular matrix. It's a singular matrix. And it has 3 eigenvalues. 0 is one of them. So you look at the residual, say 10 to the minus 8. I'm going to do gradient descent method. I do so you look at this one, epsilon equal to 1 is a 37 iteration. So you get the gradient descent method converges extremely slowly. And even with the 3x3 matrix. And you can imagine in image classification problem, because of all the translation, rotation, invariance property of the classes, how singular those things could be. Huh? For this one, it takes forever, even for a 3x3 matrix. The interesting thing is how do you fix it when epsilon equal to 0? What happens? I have talked about this example many times. I'm sure some of you have seen this. And but I insist that for the graduate student here, you should code it and also want to analyze why is the case. And the most interesting case here is that when epsilon equal to 0, and the right hand, because I'm going to look at the residual, this is in the range, you still have solution. The solution differs by constant, and it only takes 20 iterations to converge. And so what kind of message I'm giving you here? Number one is that gradient descent can be extremely slow. I don't know, the ChatGPT is a gradient descent. Somehow, Transformer, they did a good job. I have some theories, with some new theory, but this would be something to think about it. And the gradient descent method can be very slow. Another thing is about the frequency principle. I'm going to come back to this example later on to improve this method, okay? There's something called a frequency principle, which has been studied in the literature. I'm going to look at this frequency, the model problem, and let me just look at this one first. If you look at the quadratic problem, the asymmetrical positive definite matrix, you look at the analysis. It's a very simple mathematical exercise to show that because the asymmetrical positive definite, you take the eigenvectors, which form a basis, orthonormal basis. You expand it out, you do the analysis, you'll find that if you do the linear rate is the largest eigenvalue, let's say, if you order this one from lambda 1 to the lambda n is the largest, you will find the rate of convergence of the case component. The first on algebraic frequency corresponding to larger eigenvalues. Okay, I don't say the frequency here. I only say it converges to the frequency that corresponds to the larger eigenvalues. Okay. If in this particular case, if you take one of the largest eigenvalues as a linear rate, so the first one you kill the instantaneous, otherwise it's going to be converging very fast. So that's what we call some kind of frequency principle. This is a very important property of gradient descent method. Okay, it converges very fast, the fastest for the eigenvector corresponding to the larger eigenvalue. Now, what that means to the neural network later on, we're going to just see that. Let's do this one-dimensional problem, okay? In this particular case, I'm going to go back to this. Suppose this is my one-dimensional problem. I use U0 to 0 on the left-hand side, and because I'm going to use Relu, Otherwise, I want to deal with this boundary condition. Relu is 0 on the left easily. And so you look at the eigenfunction. In this case, the larger eigenvalue corresponding to high frequency. Okay, this is the PDE properties. Okay. And you can get the eigenfunctions. Now, now we're going to do this one-dimensional problem. I use this finite element. I'm going to do this linear element. Okay, I do these things here. So I'm going to do this two different kind of bases. Okay. I solve this one-dimensional two-point boundary variable problem by piecewise linear function. This time I'm going to use I'm going to use two type of basis function. First of the height basis. This is the nodal basis function everybody uses in the finite element. You get the stiffness matrix tridiagonal. Okay. So now you can see that in this case, the larger, this actually has pretty much the same eigenfunction. The larger eigenvalue corresponds to the high frequency for this particular case. And in this case, the gradient descent of the stiffness matrix converges fast for high frequency. Huh? Everybody knows this one. Okay, I think that's how the multigrade works. The convergence very slowly for the low frequency. The lowest frequency is c to the n minus negative 2. For the high frequency, it can be a constant rate of convergence, go to 0. Exponentially go to 0. That's the old stuff. Now to Relu. So Relu has you can write this this phi x is the height function in the unit interval. This is really Relu. It's a simple mathematical formula. You can write the height function in terms of 3 Relu functions. So I figure out the coefficients. You don't take a genius to do that. It's trivial. But you find it when I say 1, negative 2, 1, I got so excited. Do you like those 3 numbers? Those numbers are this stiffness matrix from these height functions. If you do that, you will find that you do a change of basis. This one looks like a negative of the stiffness matrix of the height functions. Okay, if you do that, you find something remarkable. The Relu activation function, the stiffness matrix, is the inverse of the height function stiffness matrix. Then you reverse the order, they're similar to each other. If you forget about this, reverse from 1 to n, the other one to n to 1. Okay. So what does that mean? So my Relu inverse, my Relu is pretty much the inverse of my a height function, activation function, to our old friend. So this means what is the largest? Okay, if you apply my gradient descent for this Relu business, so use the frequency principle is corresponding fastest on the eigenvectors corresponding to the largest eigenvalues. But the largest eigenvalues is the smallest eigenvalue inverse of the height activation function. The smallest inverse, whatever you have the same eigenfunction, is the lowest frequency. So what does that mean? It means that it converges very fast on the low frequency. Huh? Forget about the proof. That's what they say. Okay. For Relu, you still have this thing. Low frequency converges very fast. The lowest frequency converges exponentially fast. High frequency is this bad. It's the inverse to each other. So what does that mean? If you do a gradient descent for height function, as you can see that when you teach a multigrade method, the arrow, you get a high frequency converges fast. So that means the arrow becomes very smooth. But it doesn't really get to the original function, okay? But in most physical solutions, the profile of the physics are given by low frequency. It's a global picture. When you do image classification, you do make a difference. He's more handsome, has no wrinkle, I have wrinkles. So that's how you can tell the classification. You need a very global feature, low frequency feature. That's why machine learning is an easy job, actually. Some PDE, machine image classification is not even language, natural language processor. I think tomorrow you have this operator learning things. Suppose if you do the translation of some French to say English or Chinese, it's operator learning. You give me a vector, there's a mapping to me. That operator for me is pretty much a diagonal matrix, because you have certain words, the one-to-one correspondence. But there may be some global dependence, some grammar or something, attention or whatever, to get the global stuff. And it's much easier than our PDE job. PDE were asking too much. All right, you do solving. I shouldn't talk about too much philosophy. So I'll come back here. But okay, if you so that means if you do the gradient descent to use the finite, you don't really get the accuracy at all. You don't see the physics. But if you do the other guy, if you do the Relu, even though, how do you compare this one and that one? Physics like this one, engineer. No offense, my engineer friends here. If you look at it, oh, it looks like, oh, I got the shape right. You get the profile of the physics. That's the state of art, in my opinion, in machine learning in the whole world these days. You get this. 10 to the minus 3 or something. They call it, oh, it's good enough for me. How do you know it's good enough? Because you know the exact solution. If you know the exact solution, why do you even care to solve it? So in practice, you don't know, right? But when something converges, is that you have to be able to get as accurate as you wish. That's what I call a convergent algorithm. But my claim is that this is pretty much the state of the art. You cannot get the high frequency. Why you cannot? So what's the news? The news is that you see the profile easily, but you get the low frequency, but you cannot really get much of accuracy. And if you this is also true in the general. You want to do something in the lab this afternoon, I hope. So if you give a function, you capture the global frequency profile rather easily. But if you want to get when you say accuracy, well, numerical analysis, the accuracy is dominated by high frequency. It's a local. Depends how much accuracy you want, okay? If you want to just say, tell the difference between, a young man and an old man, you don't need much accuracy at all. In machine learning, you can do single precision, even quantum, okay? But scientific computing, you need accuracy. Now, suppose you want to, the question here is that if you want to observe some rate of convergence, which I showed you the beautiful, how do you find the n to the, so now if you do the high frequency, is the rate of convergence 1 minus 2 to the n to the minus 2. If you want that guy to be less than 10 to the minus 2, if you have 1 million neuron, okay? If you need a 1 million neuron, get a single precision accuracy, machine accuracy, 10 to the minus 7. Guess how many iterations do you want? You need 10 to the 25th iteration. That requires the largest computer in the world for 32 years to get it. So So my theory tells you that don't even think about high accuracy for numerical PDE. Unless you have different training algorithm. Or you may argue that, okay, my nonlinear problem is easier than linear problem. Do you believe that? Because I'm actually solving a linear problem, which is use Relu. Anyway, this is a biased opinion. Don't take my comments too seriously. But anyway, they say that at least from this theoretical analysis, that if you get a high frequency, get a very high accuracy, is a challenge. Yeah.
So what exactly does you re-optimize there? Is it the finite elements with value bases in the one case and with finite elements with the head bases in the other case, or do you actually?
I'm doing this for the Relu.
Okay, but you're not optimizing the weights of the neural network.
I'm actually, it's a subset of the neural network. That's the comment, that it's a linear problem. I know the W and the B, I solve for it. But if there's a magically nonlinear problem is easier than linear problem, you may beat this one. For me, that's hard to believe.
Okay, so but you're actually optimizing the neural network in the value case.
I operate the neural network by assuming that I know W and the things inside sigma W x plus B, right? I know the W and B. I only solve a linear problem, so solve for AI. Because if you give a smooth function, wow, this is a mathematical game. If I give you a smooth function, I know uniform grid is good. You know, if you take one-dimensional problem, shallow neuron is piecewise linear functions. If it's a very smooth function, okay, you tell me, I'm given some kind of lower bound in something. If you are given a smooth function, right? And if you do optimize, by the time you get it, it has to be more or less a uniform grid. So I suppose I know I give the grid, I get the way, some of the ways already you solve it. Yeah, that is always impossible problem. It's all philosophical. Maybe in practice you get lucky, but this is the mathematics. Okay, so the Relu gradient descent for Relu for scientific computing machine is tough. It's hard. That's the message I convey. I'm not saying it's impossible, but it's hard. It's more difficult than my height function. The multigrade method, and the question, the idea is you want to speed up this by multigrade method. And I'm going to come back to this example as I showed you that this is 3x3 example. I have a multigrade method for this problem. So the idea is that I take a 3 vector. This is the E1, E2, E3 of a basis function. I add this 1, 1, 1. P is the 0 eigenvectors into this. I have 4 vectors. So the 3 vector, I do the linear expansion of this 4 vectors. These 4 vectors, they are linearly dependent, right? This is P equal to E1 plus E2 plus E3. So this is what I call over-parameterization. And I write this 3 vector in terms of 4 vectors, linear combination. I call it U tilde, U1, U2, U3, U4 tilde. So this representation, as everybody here knows, is not unique. There are infinitely many possibilities. Nevertheless, I wrote this one, so I write this U equal to P times U tilde. The P is like a restriction, it's like a pulling guy. P is like a pulling. You pull this 4 vector into 3 vector. So I'm going to write this P equal to P U tilde. I have So I multiply P transpose on both sides. I get a 4x4 matrix. So U tilde is not unique. So my 4x4 matrix will be singular. But this solution is consistent. You have infinite many solutions. But after let's say assume epsilon is positive, okay? Epsilon is very small but positive, but non-zero. So but the solution, original problem has a unique solution if epsilon is positive, right? But this one has not unique, but if times Pu tilde, it becomes unique, okay? Now if you do the 4x4, I'm doing the scale, the gradient descent method. There's something magically happens. The rate of convergence, the number of iterations is independent of epsilon. So this is my explanation. Over parameterization is good. Larger language model, I don't know how many are doing LLM these days. And they do hundreds of billions. There are all kinds of explanation why you need that many parameters. At least one of my explanations, how in the world you can do gradient descent method that works so well. If you make it, instead of 3x3, you should do 4x4. In this case, it works very well. So all the preconditioned method in the world, I've been doing preconditioning in all my career, most of my career. I can interpret every precondition I invented, or all other people invented, as an over-parameterization method. Over-parameterize, you can think about you squeeze everything, that's air conditioned. If you relax, if you relax, expand it, we should be feel relaxed. Relax means it's better condition. Then you do gradient descent method that works like wonder. It's philosophical, but it's backed by many theories I've proved over the years. But anyway, but for machine learning, I believe that's me. So yeah, it's you can also do a two-grid method. You think about the 3x3, you do a pooling, get it into, or maybe you can do, in this case, you do the one. You can think about, I say, even though I did this 4x4, you can think about it recursively and do a residual correction type of thing. It's like a two-level method. It's a multigrid free. If you do the multigrid method, multigrid, if you do this basis function, usually when you do the multigrid, you do it here. You can think about this is the basis, but I can also put the cross grid basis together. This is, from there I do the 7x7, right? This is my 7-Eleven game, and it's like a grocery store 7-Eleven game. So you do 7 basis function, or you do 11 frame functions. You put 11 functions together. This 11 function are linearly dependent. If you expand this matrix in terms of this frame, the gradient descent method works like beautifully. Or you can think about, this can be true in any dimension, in any whole. Basically, instead of doing basis function, you get all this, any function you can see, you just put them in together. Any suspicious one, what I call. And you have a cost basis function, something you don't like, put them together all in there. It's in contrast with what they call deflation. If you see some bad guy, you deflate it out. I don't do it, I'm more inclusive. And diversity, DER in US, that's a buzzword these days. And you have to include everything, all the bad, the good, all the beautiful, ugly people, all together. And different color, whatever, all together. I think you do. Did I say something politically incorrect? but you put all them together. It's over parameterize it. You do relaxation method. But that's a paper of my theory about diversity. So in this case, if you do multigrade method, it works like a wonder. Okay. If you do this one here, for example, the multigrade method converge. Of course, I'm sure many of you do multigrade easily. The idea of multigrade is that a typical rate of convergence, even in machine learning, you can see loss function drops very quickly in the beginning, but outlier gets stagnated. But by the time you get stagnated, you got to do some multigrade. From there, you rescale the problems. You have some initial phase that drops very quickly, but when it slows down, you do another level. But a multigrade method converges so beautifully. My dream of the training algorithm is that I believe the ChatGPT they already have achieved these things. Otherwise, it's also reasonable because with a high over parameterization, this whole thing is rather well conditioned. If you think about it, they only use like even ImageNet. How many epoch you use to train the ImageNet? How many of you? How many epoch?
1000. 1000?
Yeah, to the ImageNet. A few hundred. A few hundred is nothing. It converges very fast for some reason. And for the language model is even simpler. Wow, if you think about all this ChatGPT, there are many others. But anyway, mathematically, it's not. They always say, "Well, it cannot be explained mathematically." Anyway, there are many interesting things. But multigrade is good. Why this? The reason I got a multigrade because I was trying to do this image classification. The image classification is that think about. How do you remember some people's face? Tell the difference between Obama and another president. This time it's politically incorrect. I guess I removed the other president, President Trump. but this one, is the kind of global features in something. You take a complicated one, you want to get a kind of low-dimensional feature. So I treat this as a linear problem. You give the image I solve for you, okay? So basically, I think about the iterative method to solve this. But I don't even know A, I treat the image classification problem as solving linear system equation. Feature extraction, U. So I basically want to extract the main feature that can be used to make the classification. That makes sense? All the other details, high frequency, I don't need them. Okay, but then you can do these things solved by. But we don't even know A, but it will be trained by the data. This will be given by the data. So basically, I reduce the image classification by solving the system equation. In this case, how do I do that? I do iterative method. If you think about a multigrade method, if you think about multigrade for Poisson equation, it's a 5-point stencil kind of convolution of that. I use a multigrade. So I have the multigrade before. So this is the multigrade method. So convolutional neural network, we have played with that. It is multigrade on the unit number of pixels. You do the pooling, okay? It is multigrade. But so you solve this equation. This is the multigrade code, standard multigrade code. From there, okay, you can think about image cosine, the stuff. So when I teach a deep learning course these days, I give my student solving PDE. There's a black one. That's the multigrade code. Then my MGNet is just maybe something even more about, there's something called a batch normalization. I don't want to tell you too much, but this actually you replace this by activation function with batch normalization. That would be my what I call MGNet. It's a multigrade. So it is identical in structure with geometrical multigrade, but all this convolution, all these things will need to be trained. And we also have some theorem which is related to what they call pre-active resonate. Kai-Ming He has this wonderful algorithm called resonate. It's considered to be a very significant step in the convolutional neural network. He introduced the resonate. If you read his original paper, he was motivated by multigrade method. All the iterative method, the way I say it is correct the residual. And but they call it skip connections, but it is correct residual. And we can actually prove that in one of the version of a multigrade or the pre-active is kind of reduced by our MGNet. And so far we have tried all this, especially ImageNet and Cepha-10, Cepha-100. I can outperform most of the existing with the same trick by like 0.5% of generalization accuracy, but not more than that. That's not so. Anyway, I think this MGNet. Okay, the reason I'm doing these things here is that image classification. There's one major step is the feature extractions. Feature extractions, in some way, is kind of most of the job is low frequency, global features. You can imagine that, right? When you remember somebody, your friend, how do you remember him? Huh? Have you asked yourself a question? I know him if I see him. There are some features that are pretty global, low frequency, I think. And but you can say that convolutional neural network are similar to multigrade. I can say it's identical to multigrade in structure. We can have, but here I don't have many hyperparameters to tune. I still strongly believe that my MGNet is better than CNN. It's probably even better than transformer. And of course, if I can beat that, then I won't be. But I actually trying to beat the transformer. For image classification, transformer is not necessarily better than CNN. I don't know, maybe somebody here, you know better here. We can, our method is very competitive for transformer. But transformer, the main application is the natural language process something. I think I also did something. Sorry, I didn't have these things here. And okay, I'm going to just pause here a little bit to summarize that. What did I say? I use this simple 3x3, 4x4 matrix again to explain how the gradient descent method actually work. How can you may improve it by over-parameterization? And then I also say that the over-parameterization can also be thought as a multi-level method, multi-grid method. Okay. Something which is CNN does. CNN, it comes with a fine grid resolution imaging. You do some polling, you do some of this iterative process. You look at all these things, some people call user dynamic system, explain this, all this sort of. For me, it's a multi-grid method, okay? You solve some kind of underlying image and feature relationship, which I give this model with unknown linear equations. For that, I use a multigrid to solve. Of course, there's something called a fully connected layer for those of you who play with it. That would be related to logistic regression, which is a statistical method, which I don't have time to talk here, is that so by doing what's the message I have here? There's something called, one of the explanations why these days machine learning can do such a good job is that most of the features are probably represented by some sort of low frequencies. And from there, you don't need this very inefficient gradient descent method that for image classification you can do a good job. For language processor, even this one of the things about the language, natural language process. Anyway, I'm new, and I only worked on this for the last 3 weeks, 3 months. It is not a unique way to say things. You can say the same thing but many different ways. It's pretty. So the accuracy, is you don't need much of accuracy, do we? And also this, if you think about it in terms of translation, voice recognition, to me that seems to be a very simple task. It's if you think about operator learning, it's like a diagram matrix in some things. Well, maybe there's some permutation, some global. But in that case, you may have a chance that. Anyway, so so I use the gradient descent type of method and to show you the behavior of it, and the multigrade method to speed it up. So I use a multigrade to do CNN, but CNN is a model. It's not an iterative method. I think ultimately I should use the multigrade to do the training, which we haven't done that yet. We're still working on it. I don't know if I have any question at this point. Okay, if not, I'm going to continue. There's something called federated learning. I want to relate. I related finite element as gradient deep learning with finite element. That's the most popular deep neural network. Relu DNA is identical to finite element. The most popular before transformer. The CNN, deep neural is CNN. I said, okay, it's a multigrade. Okay. Now, another thing which I don't know how many of you heard about federated learning. Okay. Further learning, I have my colleague at Couse saying that I think Forbes or some big magazine identifies 3 important fields. I don't know when was that to work on. The federated learning is one of them. But one of the issues here is that federated learning is that you have privacy of all your data. You don't want to share the data, but you still want to train the things. So now you collaborate somehow, don't share the data, somehow you can still train the network. And so when I look at these things, okay, it's an iterative method, then I should know a few things. Okay, now, so the way to do is this is a subspace correction method, and I probably should, how much time do I have? 10 minutes. Okay, so what I want to tell you is that there's something, the subspace correction method. And I have a CEMRACS review paper, which is my. So this is what I do here. This one. So I'm going to say that I only got 10 minutes. So basically, it's what I call we have many experts in domain decomposition. Victorita, for example, we do domain decomposition. The domain decomposition is that we decompose of a variable. You solve for AU equal to F. You decompose this space into subspace. You break the bigger space into a bunch of smaller space. So it's like the function space, X space, the way the X belongs to, right? But that's the space decomposition. Guess what the gradient descent method is doing? The stochastic gradient descent method. Anybody knows the stochastic gradient descent method? Well, of course, I'm sure everybody knows, but that's a silly question. Let me show you what the stochastic gradient descent method does. So now you have these things, okay? You do each one of the I is some data, okay? Maybe some climb. You want to discretize. What is gradient? Stochastic gradient descent method, if you think about what do you do here? So you have different client. Different client means that you have different data. It's the data, right? You have a deep neural network function there. There's also the data there. You have n data. So I call it data decomposition. You decompose the data, okay? If you do gradient descent method or the stochastic gradient descent method, basically, I just have each of the call them what a mini batch. What they call a mini batch. You do the mini batch. You do train here. You do data decomposition. Then we have something called a space decomposition, domain decomposition. Okay, what is this? So you think about gradient descent method. So what they do here, if you don't want to talk to each other, communication is the most challenging. You don't want to share your data. So what do you do here? Each one of you do some one-step gradient descent method, okay? Separately, decompose. So then you collect them together, right? Add them together. That's a one-step gradient descent method. If you do the stochastic gradient descent method, you do maybe a few clients, a few data together. So in that case, you do randomly somehow. So this is called federated learning. Now I don't know. This is just gradient descent method. What is the federated learning? Federated learning says that what if before you do the communication, what if you do more training? It's like we do subspace correction, we solve the subdomain problem more accurately. But this data, if you think about it, it's the summation of the whole thing, it's a loss function. What in the world you can solve one of them would have anything to do with the global one. But anyway, now the question, does this help? Can you train the things locally more than once or sufficiently many? Then you collect them. This is what they call federated learning. You train the things. Suppose I have n clients. Okay, you iterate 100 times. Then now you send me the data. The communication is expensive. Communication is always expensive. In this business, the number of communication is the one. You do parallel computing, for those of you, communication always expensive. And now, so what we actually found out is that, okay, it sounds like there's something called the duality. If for those of you who do the convex analysis, there's some beautiful theorems. You take a function, convex, you take a dual of it. How many of you know these things? Take a duality of a convex function. It's beautiful mathematics. And you take a duality of this. If you take the dual of the things, so it turns out data decomposition, the dual of that is space decomposition. That's what so we actually realize that we understand if you write this federated learning tensor, I can be mathematically equivalent to a dual problems. And in that dual problem, I do a space decomposition or domain decomposition for that problem. Because that one is this x, okay, this variable x. Otherwise, the theta, WB, AI, that kind of things. Then you have the data, of course. And for doing that, you can have we can have there's some algorithm here. It's kind of complicated, but it's not exactly what it does there. But you can have some kind of a data introduce this. In this case, you need you need this extra variable to make it work. By doing so, we are able to prove that if without by certain number of iteration, you need this many this is like the condition number of the, we can only prove for convex problem, and you can get to square root. It's like the conjugate gradient method. And this acceleration techniques in machine learning, which are relevant here. But anyway, I just want to use this example to show you that, okay, there's another guy called federal linear. Somehow many people are interested. Then I can say, okay, it's equivalent to our domain decomposition stuff. I just use this as an example to show you. And anyway, I just summarize that in this lecture, I did iterative method, frequency principle, then over-parameterization, and also in the end, I touch upon the subject called federative learning, which can be equivalent or related to our domain decomposition. All right, thank you.
Okay, we still have time for a few questions.
Well, thank you for your talk. I have a question concerning the Poisson problem, let's say. So when you use a neural network to represent the function, but then to get the linear system, let's say, you use the Galerkin method, if I am right.
Yeah.
And many people in the PIN community try to build a neural network that will mimic somehow the mass metrics, sorry, the stiffness metrics. So am I right? Can you comment on that and so on?
Yeah, in this case, I use Relu this is a linear problem. I solve a trivial problem by a trivial method to see where the difficulty comes from. So by ignoring the nonlinearity, I replace the height function, which is a classical method to do, by the Relu. So I see this frequency principle converges very slowly for high frequency. I do not know if I answer your question that if for your question that if in general, if you do the neural network, you do not have a stiffness matrix anymore for neural network method.
Yes, and usually people don't try to build it.
You don't have that one. You do a quadratic, you do a loss function minimization. Yes. But this one also has it. You also the linear variational Galerkin method. You do a minimization of this quadratic form, which is the loss function. Okay.
So another way to ask my question: could you do the same with the neural network language? If I mean.
I could, but basically my message is negative because yes, that's the whole idea. And you can, actually in this afternoon's session, I do the L2 fitting, you do neural network, you see the frequency principle, you capture the low frequency rather easily, you cannot capture the high frequency easily. Yes, the answer is that you do the minimization problem in this case. I also do the minimization problem for the linear case. In that case, it's quadratic, which is convex. In this case, it's a non-convex, non-linear problem. Yes, the answer is that you have the same phenomena, and you have the low frequency where converges relatively fast. The high frequency is hopeless.
Other questions? So if not, let's all go to the lunch and we will meet here at 2 p.m.
Okay.